All right, so this will be our first post-midterm lecture building on the content that we saw before the midterm. And I would also say that my general advice for how to approach this going forward stays the same. Your best study strategy is to read the textbook, then access this lecture, listen to that, and then go back and read the textbook again. That is the best strategy no matter how we are holding this class. And also, if you still have questions about anything after that, get in touch with myself or your teaching assistants, and we'll be happy to help you understand these concepts better. I'd also add that I hope that, as you're following news coverage about this entire public health crisis, you're really appreciating the role that statistics and data are playing in this in helping us understand the nature and spread of this disease, and also some of the interesting questions we're having right now about the quality of the data that we do have and how certain we can be in the projections that we're making about what this will look like in a week or a month from now. A lot of the dialogue that we're having at the moment is really about statistics and its nature, and also the degree of uncertainty in statistics. It's all getting a lot of attention right now. So I hope that if nothing else comes out of this for you, you are really gaining an appreciation for the role that statistics plays in science and public health, and how difficult it can be to convey statistics in the media. It's really interesting to be watching right now. So think about that as we progress through the next several months. So moving forward into this lecture, we're starting to make the transition between the more conceptual part of this class into the much more quantitative part of this class. And so this lecture is about statistical inference. And so the things I want to hit on in this lecture will be things like understanding the logic of statistical inference in samples and populations, understanding the application of the central limit theorem, understanding standard error, and also understanding how to calculate a confidence interval. Those are all things that you will understand by the end of this lecture. So as I said, we are getting into the more quantitative and mathematical part of this course. So just to think about where we have been, the first part of this class focused a lot on research design, where we talked about theory and concepts, measurements, variables, dispersion, what a hypothesis is, and different approaches to research. And these concepts are really critical for understanding what good research is and how to do more advanced statistics. It really would not start much sense to start to begin this class back in January with the math, because you really have to understand the logic of how that math is being used, why it's being used in a certain way, before we can really get into the formulas and the statistical element of this class. So hopefully you have a good foundation in that. And now we can transition into the foundations of the math of statistics, which is really about using data to make mathematical inferences, which then in subsequent weeks is going to get us into talking about statistical significance, correlation, and regression. But let's start the class on the next slide with something that you might understand a little bit better as political science majors. So we're in the middle of election season right now, a very interesting election season, but for much of the last year, we've had a lot of polling thrown at us about candidates and how well they're doing. What Democrat, for example, polls the best against Donald Trump. And obviously there's a lot of uncertainty in all of that polling because there's a lot of campaign that hasn't happened yet. But this kind of discussion that we're seeing about polling and data is nothing new in campaigns. So here from 2012, it's an older but good poll. We have a poll from March 2011. We had a bit of the opposite situation. We had a Democratic incumbent, Barack Obama, who was running for re-election, and we had a number of Republicans who were either running against him or thinking about running against him. And Newsweek and Daily Beast did a poll in March 2011 polling Obama against some of those potential opponents. So you see here, for example, that when tested against Mitt Romney, Obama led Romney by 2 points, 49 to 47. Obama scored the same as Mike Huckabee, 46-46. Obama had an 11-point lead over Sarah Palin, who was considering running in 2012. She ultimately didn't. She didn't get much past the exploratory phase, but she did start that process. And then Donald Trump, who was talking about running, threatened to run, but never actually pulled the trigger on that. Obama had a 2-point lead over Donald Trump, 43 to 41. So we have 4 different matchups here of Obama with different Republican candidates and different numbers for each of these. And the article that I pulled this from talked about how Obama was narrowly leading Romney, but was tied with Mike Huckabee, right? So look back to the poll, Obama 49-47 over Romney, so a narrow 2-point lead, but scores the exact same as Mike Huckabee, 46-46. Interestingly, Barack Obama's vote share is actually a bit higher against Romney than it is against Huckabee, but that was the headline, that Obama narrowly led Romney, but was in a tie with Huckabee. And so what we want to be able to learn about in this lecture is to ask, well, how fair of a statement is that? How fair or accurate is it to say that Obama really leads Romney, or Obama is really tied with Huckabee? So as people who are becoming knowledgeable about statistics, what we need to ask in order to assess that fairness is what needs to be considered if we want to be able to draw conclusions about the population of interest from a sample of respondents. So here we have a sample of potential voters. We want to speak about a potential electorate. So we should start thinking, well, what do we need to know? What do we need to ask about these data in order to understand the projections, the inferences that are coming out of this, and how we can speak about these intelligently? Let me take a moment on this slide to actually define what statistical inference is before I get more into talking about it. Statistical inference, quite simply, is the practice of using data from a sample and the rules of probability to make careful statements about the population that the sample was drawn from, and to quantify our uncertainty about those statements. And that is what statistical inference is. And I've already talked about that in this class, that when we do a survey, for example, we want to use a random sample of some kind to interview a subset or a smaller portion of the population that we're interested in talking about. Remember how when I talked about sample sizes, for example, that we might interview 300 or 500 or 1,000 Americans in order to make an inference about 330 million Americans who we can't largely talk to. That's what statistical inference is. If we have a well-drawn sample, even if it's under 1,000 people, statistical inference is what allows us to take that sample of smaller people and then make statements about all those 330 million people that we weren't able to interview. But also critical to that is to be able to incorporate a discussion of uncertainty. Remember how I've talked about that the stupid way to interpret a poll is to look at a poll and say, the poll says X% of the public thinks this, so that must be the absolute truth. No, that's not the correct way to interpret a poll. We've discussed that. The correct way to interpret that poll is to say, the poll says X% of the public thinks this. How uncertain are we about that? What's our margin of error? What kind of error is built into this, right? What range of real possible values are we talking about? And that's really talking about the uncertainty that we're going to quantify in this lecture. So you've already really been exposed to what statistical inference is, and this is really just the formal definition of that. So let's go back to our poll that we just talked about. We were asking about how we can make fair statements about this poll. The first thing that we would really need to ask is how the poll was conducted. And I've talked a little bit about polling, about sampling, not polling, I've talked about polling too. talked a little bit about sampling. I'm not going to go into incredible detail about all the different ways that you can do this, but it is important to address sampling to a degree because it is critical for statistics. Much of the math of statistics is based on the math of what we call the simple random sample that I've talked about in this class already. If you recall, the simple random sample is where in an ideal world, we have a list of everyone who is in our potential population, and then we sample randomly from that list, so that ideally everyone has an equal and known probability of being in our survey. So you might imagine, for example, let's say I wanted to do a survey of KU students, or about 20,000 students at KU. There's an actual list that exists of them somewhere, with phone numbers and email addresses. And you might imagine that instead of talking to all 20,000 or whatever of them, I might want to do a survey of 500 of them. So in an ideal world, how that simple random sample would work is that I'd have maybe a spreadsheet with all those phone numbers or all those email addresses in them, and I'd assign every student a number, and then I'd use a random number generator. I like to use the website random.org. There are lots of resources out there for that, but I might use a random number generator to generate a random list of 500 numbers between 1 and 20,000. If we imagine there are just 20,000 students. And then whoever's numbers are pulled out is going to be in my survey. So if number 10,001 is selected by the random number generator, then whatever student is number 10,001 on my list of students would be selected for my survey, and hopefully they would participate. So that's the basic logic of a simple random sample again. And in the real world, there are a lot of variations of that. And obviously, we don't have a list of all Americans, but we can still do reasonably good samples, even though we don't have that. If you're really interested in all of the different variations of this, there is a survey research class that I teach, and sometimes Professor Mullenix teaches every now and then, and we'll talk more about that in that class. But that basic math of the simple random sample, it grew up with statistics. It grew up with surveys and probability. And a lot of our math of statistics that we're learning here is really based on that assumption of randomness and the simple random sample. So if we're going to assess this poll, the first thing that we need to ask is, well, how was the poll conducted? And hopefully there is an acceptable variant of a simple random sample that was used to do this survey. If a variation of that was not used, then this survey is trash and we can't talk about it. Fortunately, in this survey, a variation of simple random sampling was in fact used, so we can proceed to talk about it statistically. And so we know that a random sample of likely voters identified in some way was used in this survey, so it passes that first test. I'm just giving you that information. How confident can we be then that support for Obama was really more than it was for Romney or tied with Huckabee and so forth? How confident can we be that these numbers that we see here really describe what's happening in the population that we can't talk to, all those people we can't talk to? How confident can we be that these are good data to make projections for about the larger population? And then how can we talk about those projections intelligently? So that's what statistical inference is allowing us to do. A little bit more of a review on this page, but again, hitting some necessary points. So again, it is possible to get a good idea in a public opinion survey, for example, about what over 300 million Americans think by asking just a few hundred people. And remember what we talked about before the break about why we typically don't see samples with thousands and thousands of people in them. You might go back to that slide in, I believe, 2 lectures before the break, where I talked about the diminishing marginal returns that come in reducing error in a survey, and how 500 people is going to bring you significantly less error than 300, or 1,000 will bring you significantly less error than 500. But really, when we get beyond 1,000 people in a survey, we don't have substantial decline in the error, the margin of error, for example, that comes into a survey. So that's why we very rarely see public opinion polls in the United States that are over 1,000 people, because as a pollster, you're really wasting your money. Your bang for your buck in terms of getting more accurate estimates really diminishes beyond 1,000, and it's not worth your money to go to 1,500 or 2,000 people typically. So, when we talk about sampling, again, just to refresh our memories, in general, yes, larger samples are better, but beyond a certain point, typically 1,000 people, the marginal improvement is minimal. So a lot of the surveys that we will consume as citizens will be under 1,000 people, and that's fine. You're dealing with the ANES in this class, which has many more than 1,000 people, and that's okay. But even though it's a substantially larger sample, it's important to think about what you're really getting from that. Let's say you take a survey like the ANES. Let's imagine it has 5,000 people in it, right? What do you get out of a survey for 5,000 people versus 1,000 people? Well, what you're not going to get out of that is a substantially larger reduction in error when you're talking about the general population, right? Because you do have those diminishing marginal returns past the point of, say, 1,000 people. So all things equal, a 5,000 person survey of the American public is not that much better than a 1,000 person survey. But what you will get in a 5,000 person survey is you're going to get a lot more people who are in different subgroups in the population. So in a survey of 5,000 people, for example, you're going to get more African Americans, more Catholics, more college-educated women, more people in any smaller group in that larger survey than you would be getting in a survey of just 1,000 people. So what actually you do get, with the gain you get in that survey of 5,000 people, is better data on subgroups in the population. We can actually get a better sense of what African Americans think in a survey of 5,000 people versus 1,000 people, because all things equal, there are more Black respondents in a survey of 5,000 people. So we get a better way of talking about subgroups, even if when we're thinking about inferring to the population overall, we're not really getting a much smaller degree of error. So, just to think about that, and again, we've talked about this before, larger is better, but there are limits on that. But larger can be better when we're talking about smaller subsets of the population. But I want to, get it in your head right now that, again, that error is going to be very important, and thinking about error is very important, and thinking about how we can use error to have confidence in the inferences that we make from samples is really where we're going in this lecture. And getting you to that point is going to take a bit of work over the next several slides, but let's start talking about that. So let's start taking this down a bit more of a mathematical route and getting you into some of those concepts. So let's say that we have a sample. The probability theory provides the mathematical and theoretical connection between the data that you see, which is the sample, and either the complete collection from which they come, which is the population, or the underlying process that generated the data. And the theory of probability connects those two things and allows us to quantify our uncertainty about what we have learned from the sample. So what's all this mean in English? That if we have a sample that's drawn in a certain way, typically a simple random sample, there are certain properties of that sample that allow us to quantify our uncertainty in talking about the broader population. There are also certain properties of that sample that allow us to understand the math of how that sample was generated. A lot of this math element right here is stuff that I'm not going to get into in this course, but if you go on to graduate school and you have to take a statistics class, you're actually going to probably have to be exposed to a lot of this math and to understand it. But I think an important point for you to grasp from this right here, even if we're not getting into probability theory and functions and formulas in that, is that the math of statistics is really based oftentimes on the assumption that our sample is generated through a random process, a simple random sample. And a simple random sample has certain mathematical properties that then lead to everything else that we're talking about here. Margin of error in a poll, confidence intervals, for example. So if we have a sample that's drawn in a certain way, we can use the mathematical properties of the simple random sample to then inform how uncertain we should be in talking about the population. Let me talk a little bit more about the random sample, and some of this will be, again, stuff I said already in this lecture. A simple random sample is one in which every possible sample has an equal chance of being chosen, because every person in the population has an equal chance of being chosen. So if you go back to the example of, let's say that there are 20,000 students at KU, and I want to survey 500 of them. If I have a list of all 20,000 and I draw randomly from that list, we know what the chance is that any single student will be in my sample. It's 1 over 20,000. And we know that that chance, that probability, is equal for every student in the population. Every student has a 1 over 20,000 chance of being in my sample if that's how I'm going to be able to draw it. So right there, you have a basic mathematical point of what an individual's probability of being selected is. You have a second point that every individual has an equal mathematical probability. Furthermore, we know that every possible combination of 500 people has an equal chance of being selected as well, because every individual has an equal chance of being selected. So that's a third mathematical property that we have right there, that can allow us to then build some formulas to then talk later about uncertainty. Obviously, if you imagine the scenario that I just gave to you, it is often impossible or impractical to do a simple random sample. But it is typically the starting point for thinking about how sampling is done. There are other types of sampling that are okay to use, such as stratified samples, where we might divide the population into different groups and then sample from within those groups. There's the clustered random sample, which is what the ANES is. It's clustered on geography in the face-to-face interviews, which lowers costs, or some combination of those. So a lot of good surveys that we'll see are not necessarily pure simple random samples, but they're going to be variations of that. Variations that are not too far away so that we can continue to use those basic mathematical properties of the simple random sample to then inform how we talk about uncertainty. And so obviously, again, why would you want a random sample? The short answer is that the relative frequency distribution for a data set will approximate the probability distribution of a population, which in English means that your sample will look like your population ideally. If I take a sample of 500 KU students, ideally, if that population is randomly drawn, those 500 students will look like all 1,000. If I take a sample of 1,000 Americans that's randomly drawn, ideally that sample of 1,000 will look like all 330 million, ideally. Later in this lecture, we'll talk a little bit more about how that can actually go wrong and why a lot of samples are better than just one. But at least in theory, a random sample is going to give us a sample that looks like the population that we're trying to talk about that we can't observe. If you think about it, that is also a mathematical property, right? We're assuming that the properties of the sample are equal to the properties of the population. So just here on this one slide, if we're thinking about probability theory, there are four mathematical properties that we've seen just here on this slide that we can use to begin to construct some math that allows us to talk about a population from just a sample. And obviously here the point at the end that if we have a systematic sample where we're choosing people in some systematic or non-random way, or if we have a non-random sample like just taking people through a convenience sample, that can introduce a lot of bias. So all of these assumptions here that we've talked about on this slide, for example, the assumption that everyone has an equal chance of being selected, the assumption that the sample looks like the population, the assumption that every possible sample has an equal chance of being selected, all of those assumptions fall apart in a systematic sample or a convenience non-random sample because there's so much bias that's introduced that our mathematical assumptions disappear. So, this slide, very important for introducing to you some of the assumptions mathematically that come with the random sample that allow us to build up to doing some math later in this lecture. Here on this slide, I'm just restating for you what I already discussed earlier. Maybe talked about a little too early about what comes from a large sample and what doesn't come from that, but I've already discussed this. And for those who might still be a little confused about what we mean by randomness, let me talk about that a little more on this slide. What do we not mean by random? So we don't mean the street definition of random. So oftentimes when we use the word random in just casual language, we might mean that something is haphazard or chaotic. That's not what we mean in a random sample. We're also not meaning something that is completely unknowable. If you think back to what I talked about on the slide earlier about mathematical properties, random samples have mathematical properties that we can know and do know, and we build statistics on those assumptions. So in a mathematical sense, in a statistical sense, by randomness, what we mean typically, what we more mean is without a defined pattern or order. And that is really the statistical definition of randomness. And so if we think about a random sample, for example, a single observation may be unknown in the sense that we don't observe all single members of the population. We don't know per se if a member of the population will end up in our sample, but we can use the properties of a random sample to say something about how likely it is we are to see certain population members, certain values come up in our sample, and the distribution of a number of observations. So again, coming back to the idea that there are things that we actually do know about a random sample in terms of its mathematical assumptions, as I've already discussed in this lecture. And those assumptions are incredibly important for then letting us talk about the population that we can't observe. So as I said, you might not realize it yet, but I have secretly snuck in already 4 mathematical formulas that I didn't actually show you. and then I'm not going to prove for you mathematically. You can do that in grad school. I've actually already snuck 4 mathematical formulas into this lecture that hopefully you picked up on already about the properties of a random sample. So let me push that a little bit more and introduce to you something called the central limit theorem, which is built on those mathematical formulas that I secretly just taught you. I think this is something that some of you have heard about before. And I think that the way that you have often heard about it is that when a sample starts to reach 30 people, it begins to look like what the population looks like. And I think that's the way that it often gets taught to you, especially in high school, if you're ever exposed to this. Um, that is not inherently wrong, but that's not the way that I'm per se going to talk about it in this class. So let's stick that aside for a second, compartmentalize that if you've already heard that about the central limit theorem, and let me hit separately on 2 different properties of the central limit theorem that are going to be important for this class. And I'll deal with these properties separately. I'll have a separate slide later where it's the same thing as we see here, but I'll deal with the part that's in black. So let's first deal with the part that's in red. So this says that if we were to take many random samples of some size n from a population, and we're measuring something with a mean of mu in the population and calculating the sample mean x bar for each sample, let's stop there because I knew I just threw a lot at you. All right, what are these letters? N, you've seen this before, is a sample size. Let's say that we're measuring some variable, Donald Trump's job approval, for example. Donald Trump, if we're to say that's our variable, has a true job approval in the population that we cannot observe. We can't talk to 330 million Americans and ask them if they approve or disapprove of the job that Donald Trump is doing. But if we were to do that, let's imagine that we could somehow do that. We have magical powers. Donald Trump would have a true job approval out there in the population. That, again, to use language that you've seen, is what we call the population parameter. We cannot observe that. We cannot observe Donald Trump's job approval population parameter because we can't talk to 330 million Americans. But we give it a letter, and it's called mu, right? So mu is Donald Trump's true job approval out there in the population of people that we can't talk to. We want to be able to make an estimate about what mu is, but we can't talk to the population. We have to use our samples to make inferences about what mu is. And so in the sample, let's say we did a survey and it has a sample of however many people in it. We can ask that sample if they approve or just disapprove of the job that Donald Trump is doing. And in the sample, Donald Trump's job approval would be X bar, right? So that is the sample mean, his average approval in the in the sample that we're talking to, all right? So N is sample size, mu is the unknowable population parameter for some variable, and X bar is the measure of that variable that we see in our sample. And we're going to use X bar to make an inference about what mu is that we can't observe. So let's go back here. So if we're to take many random samples of size n from a population, and that population has a mu that we can't observe, but we can measure X bar of whatever variable we're talking about in a sample, we've taken a bunch of samples now. So the central limit theorem tells us that the average of all the X bars in our samples would equal mu. Well, what's that mean? Let's say I have 10 samples that I've taken, and Donald Trump's job approval in those samples ranges anywhere from 40 to 50%. So the central limit theorem tells us that if we're to average all of those Trump job approval numbers in our surveys and come up with the average, that the average is going to be reasonably equal to mu. Well, what have you learned just from that statement? It's telling us that more samples is better than one, right? So think about this. If we have 10 surveys and Donald Trump's job approval is 40 to 50, right, in those surveys, we have some variation in that. We have a 10-point range in those surveys. And so obviously there is a mu out there in the population, and that mu is precise. We just don't know it. But we have different surveys that are hopefully dancing around what mu is. Let's say, for example, imagine we actually knew what mu was. Imagine that it's 45%. I have magical powers, and I can read the minds of all Americans, and I know that 45% of them approve of Donald Trump right now. All right, but my 10 surveys give me anywhere from 40 to 50. So I have some surveys that are obviously off by up to 5 points. Maybe I have some surveys that tell me Trump's job approval is 45, 44, 46. Those are closer, right? So this first statement here is telling us that we're going to get a more accurate estimate of mu, that 45%, if we average all of our samples instead of just use one sample. And we typically would see that that would be the case in those rare instances where we actually know what mu actually is. So a second statement here is that the standard deviation of the x bar would be s sub x bar. That's a subscript, but the bar looks a little funky. And the histogram of all of that would look like a normal distribution or a bell curve. So we've given a name here to the standard deviation of x bar, and we're assuming that if we're to graph all of our x bars, that it would look something like a bell curve. So let's proceed forward and see what this looks like in practice. So let's illustrate what I just showed you. And I'm actually borrowing this from a friend of mine who teaches statistics at a different university. And this is something that she actually did and quantified just to show the central limit theorem working as I just described in practice. So I am borrowing this from her, and this is actually a real example using real data. So to put this in a context that we might grasp, since we did just have an exam in this class, let's imagine that I have 200 people in this class, and so that I have 200 test scores. She actually had 200 people in her class. That's where that comes from. And let's say that I write each test score on a square of paper and put those squares into a bag or a bowl or whatever. So I have a bag, a bowl, I have 200 pieces of paper in there, and I have each person's test score on a piece of paper, right? So every test score is in that bag or bowl. Let's also imagine that the mean of the population of all 200 test scores is an 80.25. So when my friend actually gave her exam to her class of 200 people, the class's average was an 80.25. So if you imagine here what we're talking about with the central limit theorem, we have a small population here where we actually know what mu is. We know what the population parameter is. The average test score for the entire class is an 80.3. Right? So we've created a situation here where we actually know what mu is, which is very useful for illustrating the central limit theorem. Now let's say that I randomly, and I put that in quotation marks because, pulling names or paper out of a hat or a bag or whatever, it's not exactly random, but let's imagine that that's random. Let's say that I randomly pull 20 test scores out of the bag. So in other words, I'm taking a sample of 20 test scores, and then I calculate the mean test score for each sample of 20, and then I repeat that until I have 10 samples of 20 and so 10 sample means. And my friend did this, and she graphed it over here on the right. Actually, rather than doing this, pulling it out by hand, she actually had a computer randomly pull out samples of 20. Yeah, that's an option as well. So if we take these 10 samples, and each sample has 20 test scores, and we graph that on the right, we see that not every sample perfectly recovers mu. Or in other words, the average test score in each sample is not 80.3, our population parameter. Instead, we see that we're dancing around it on either side. We have one sample where the test score was 77. We have the average test score was 77. We have two samples where the average test score was 78. Fortunately here, our modal response, our modal score of 80, the population parameter, was seen in the most samples of 3, but we also had a sample, for example, that had an average score of 82, right? So here we're seeing what I illustrated for you earlier, that if I take repeated samples from the population, not every sample is perfectly going to recover mu. And here again is a weird case where we know mu. But at least we can see here, by taking these random samples, that we're not too far from mu, and we're dancing around mu, a little bit on the left and a little bit to the right. We don't have, luckily, any samples here where we are significantly off. At most, we're off by 3 on the average here. Now, let's take more samples. Let's say I get really bored and I take 100 samples out of my bag of 20 observations each, then 1,000, then 10,000, then 100,000. This is obviously really hard to do by hand, but you can do this very quickly and very easily with a computer, as my friend did with her class's scores. And then we graph all of these into a histogram. Here you can see, going from left to right, we have histograms that have gradually more and more samples in them. 100, 1,000, 10,000, 100,000. There are certain things that you can see here. One is that as we get more samples in the population, the histogram starts to look more like a bell curve. And that's pretty well illustrated here, especially if you compare 100 to 100,000. Notice a second thing, that the bell curve seems to center on mu, right? So we're seeing here, on average, our samples are recovering mu, even if some of our samples are a little bit off. So you can see, for example, here, thinking about, well, if our modal response is typically mu, and if on average we seem to be recovering mu with our samples, our large body of samples, maybe if we average all of them out, they'll actually reflect mu. Maybe. We'll see that on the next slide. You're also seeing something else here about outliers. So look over here, for example, at the graph of just 100 samples. You see on the right that you have one rather unusual sample here, where the average test score in that group of 20 scores was 85. So it was 5 points above mu. That's 5 points off. So let's think about that for a second. Let's say that was the only sample that you bothered to draw, all right? If that is the only sample that you bother to draw, and you see that the average test score is 85, you would say, well, I would guess that the average test score in the entire class was 85. You wouldn't actually know, if you don't know mu, you wouldn't actually know that in reality you've overestimated the class average by 5 points. So you have an outlier here, but you can't tell that because you only have one sample. But if you're to take repeated samples and then plot those samples, you can begin to see that in reality, oh, that 85 actually looks like an outlier. And you can see here, even in the histograms of 10,000 or 100,000, that they have very skinny tails on the left and the right. So, if we have a test score that's 72, 75, 85, or 90, we might actually see those in a sample. But the way that we know that they are outliers is by taking repeated samples. So we can see what that histogram actually looks like and what the typical responses actually look like. And if you're someone who you follow me on Twitter, which some of you do, some of you don't, but one thing that I say on there oftentimes is that if I have an interesting poll that I want to talk about of like an election in Kansas, I'll say, well, this is just one poll, and we'll get a better sense of what a race looks like the more polling that we get, right? So more polls is better than fewer polls. 3 is better than 1. 5 is better than 1. 10 is better than 3 or 1. Well, now you can see why I say that. If we are polling an election and all we have is just one poll, that poll could be perfectly accurate. It could perfectly reflect what mu is, or it could be an outlier. But we have no way to know whether that poll looks typical or whether it looks abnormal unless we take more polls. So if I get a poll today with horse race numbers on an election, I can say, well, this is interesting. This is what the poll says. Let's see what more polling says. If the next poll and the next poll and the next poll look reasonably like that first poll, then I can say, well, okay, we now have a number of polls here that tell me that a candidate might be ahead or that they might be reasonably tied. And so the more polling we have, the more confident that we can be in what the race actually looks like. But if I get at one poll and then the next few polls look nothing like that poll, then I might start to say, well, okay, it looks like that first poll we got might have been an outlier in some way. That doesn't mean that the poll was done badly. Just like you see here, you can get outliers that aren't really reflecting mu. That doesn't mean that they're badly done samples. But you get a better perspective on that one poll the more polling that you get. So that's an interesting third thing that you see here, that when you get more polls in a group, you start to really be able to tell what the outliers are and what the typical response is. If you're into following election polling, this is also the logic of averaging polls and why typically averaging polls is better than looking at one poll. Because when you average polls, outliers get washed out. An outlier in any of these histograms is going to have a lot less influence on the average than that bulk of polls that are closer to mu. So this is why we typically look at polling averages in elections, because they're neutralizing the effect of outliers and they're hopefully giving us a more accurate picture of the race. So here again, you're seeing more of the central limit theorem illustrated. Here what we do, actually what my friend did is she figured out the mean of the means, or the average of the averages. So each sample had an average, right? And now she's looking in each grouping of 10, 100, and so on, and then looking at the averages of those. So in that first 10 samples that she took, the average test score was 80.3, which was basically mu, and it's also basically the same average that you get when you took 100,000. So the population mean was 80.3, and we got pretty close with even the smallest sample of 10 samples. got marginally closer with larger samples, but it really wasn't worth my time to do that. It didn't yield greater accuracy. But at least with this, you're able to see that when you have more data points to plot, you get a nicer bell curve, you get a better perspective on outliers. And you see also that even with the smaller sample here, you got a pretty accurate estimate of what mu was. Let's push this math a little further now. You have seen so far in talking about central limit theorem that we can do a very well executed random sample, and that random sample may not recover the population parameter. So we can do a sample of size n, and x bar might not reflect mu, if we're to bring back some of those notations that we saw earlier. But on average, though, when we look across samples, if we draw samples in a random way, we'll generally recover mu. But again, you've seen here that we can have outliers. We can be off just by random chance. And so this is a good opportunity for us to go back and revisit the difference between bias and error that we've talked about so far in the class, especially because we're now going to push the central limit theorem to where it can help us estimate error. But let's make sure that we understand the difference between bias and error first. So think about what I just talked about, how you can do a random sample, and just by chance you could be off. You could miss the population parameter by a few points just by chance. There's nothing systematic. There's nothing biased inherently that went into that. It's just that we didn't recover the population parameter perfectly, even if we were in the ballpark. So that kind of non-systematic, random missing is what we tend to think of as error. And that's what I'll focus on mostly in the rest of this lecture. But let's distinguish that from bias. So bias in estimating a population parameter occurs if across independent replications of a sample or some estimation procedure, we would over or underestimate the population parameter. So think about what we just saw with central limit theorem. We did a lot of samples, but on average, we captured mu. What if we did a lot of samples, and on average, we missed mu? We were too high or too low. Our average scores in our sampling were above or below what the average scores were in the class, or we over or underestimated Donald Trump's job approval, for example, systematically and consistently. That would be bias. And so bias can come from a variety of sources which are more systematic and that we've already talked about to an extent in this class. One of these might be selection bias, for example, which refers to the likelihood of even being included in the sample. So we've talked about coverage error, for example, where in some states, if we are doing a survey, we can't legally survey cell phones. And cell phone populations often tend towards, cell phone only populations rather, tend towards younger Americans, poorer Americans, minority Americans, individuals who often are more democratic or liberal in their voting preferences. And so if we can't survey a chunk of the population that's cell phone only, and they're off limits to us, that's coverage error. But the bias comes from the fact that that population might be different from the population that I can interview. So again, I always like to use the case of North Carolina here. North Carolina is a swing state, but in North Carolina, you can't survey cell phones legally. And so in North Carolina, because you're systematically unable to interview a chunk of the population that skews more democratic, something we often see in North Carolina polls is that they often tend to underestimate the Democratic vote. We see the same thing in Nevada, which is another swing state where we can't survey cell phones legally under most circumstances in that state. And so that really comes back to coverage error, where it can be hard to do a random sample well if we are systematically missing a chunk of the population that is different from the people that I can talk to. That in this case leaves me with samples that might skew more Republican. So that's systematically missing a chunk of the population, and that is bias. Another example of this that you've seen is the problem with defining who is a likely voter in a poll. Sometimes we have a likely voter screen where we filter out too many or too few people, and that can impact systematically whether our poll might be a little more favorable to the Republicans or the Democrats than maybe it should have been. So there are definitely some issues with systematic bias that are systematic, they are identifiable, they exclude a chunk of the population, and because that chunk of the population is different, they shift our average, they shift our estimate of mu. So that would be bias. Response bias also factors into this, and this is referring to the likelihood that someone answers a survey or answers a question. So think of the types of non-response error that I talked about before in the midterm, where certain types of individuals are more likely to answer a survey versus others. So in the typical raw survey data, we typically have too many women, too many white people, too many people of middle income and education. Middle-class white women are often our most common survey respondent and overrepresented, often significantly in surveys, meaning we're not getting enough younger people, we're not getting enough minorities, we're not getting enough people at the high and the low end of the education spectrum. So even in that case of who we're getting into our survey, we're systematically missing certain types of individuals. Or think of the example of racial attitudes I gave you before, where oftentimes the people with the most racially hostile attitudes, they don't want to answer questions about race. So because they don't give us an answer, the attitudes that we do have on a lot of attitudes about racial affairs, racial matters, or policy dealing with race, they often look less racist, less racially antagonistic. So all of this would be bias. All of this is bias that systematically makes a sample different from a population. All of these systematic sources of biases mean that our estimate of the population parameter, our X bar, might be off from mu. And this is something that we want to try to eliminate in surveys. And that there are a lot of strategies that we can use to try to eliminate these forms of bias. But I want to say very clearly, bias is different from error, right? Everything here I've talked about with selection bias and response bias, that's bias. That's not what error is. Error is what you saw earlier, where we can take a good sample and we might miss mu by a little bit just by chance. So one of these is systematic, one is random. One we can try to eliminate, the other you can't eliminate. And that's what I want to talk about next. So let's pick up on what I just said, that eliminating bias does not eliminate error. We can eliminate or try to eliminate those systematic sources of bias that I identified on the previous slide, but that doesn't mean that our sample will always recover the population parameter perfectly, just like what you saw again when we took quality, perfectly fine random samples, but we were off from the population parameter by a few points when we were trying to find the class average test score. So eliminating bias does not eliminate error. But the advantage of error, the good thing about error, is that error from random sampling, that we call random sampling error, does tend to be easier to deal with than systematic bias. Because randomness, if you think about it, actually has some properties to it that we can estimate mathematically and deal with mathematically, and also know mathematically. So because we understand randomness, dealing with error that is random is actually something that we can accommodate through math. And again, this is one of those points where I'm sneaking some math in here that I'm not actually showing you. But again, go into grad school, you'll actually do the proofs, I'm sure. So let's talk about random sampling error. So random sampling error is the extent to which a sample statistic, or an X bar, varies by chance from a population parameter, or a mu. Again, you saw this. We took samples of test scores. The class average was 80, but maybe our sample said it was 77 or 84. Just by chance, we didn't have an average of 80 in our sample. That would be random sampling error. So given that we have a random sample, we can actually begin to think of this in terms of a formula. So that if we're estimating a parameter, we can think of that estimate as a sample statistic plus random sampling error. Or in this case, mu equals mu hat plus epsilon. Mu hat is something that in Greek notation, we often use to represent an estimate of a population parameter. This would actually be the same thing as X bar. Unfortunately, I did not develop the rules of Greek notation and statistics, and this is one of those cases where two different things can mean the same thing, but just understand here that our estimate of a population parameter is a function of what our sample statistic says plus a degree of random sampling error. That's often hard to know, but we can estimate it. So if we think about what affects the size of random sampling error, and things we might talk about in going forward in this lecture, two things would be sample size and the variability of the attribute under study. So if we're studying a test score, if we're studying Donald Trump's job approval, how much variation is there in that? And those two things are going to be the biggest ingredients in really estimating the size of random sampling error. So let me introduce a formula to you here. This formula comes from all of the math that I actually just talked about, but spared showing you. Particularly the math about the properties of randomness and random samples. But thanks to statisticians, given all of that, I can show you a relatively simple formula to estimate random sampling error. And so conceptually, we can think of this formula as expected sampling error. So by that I mean the random sampling error that I expect, the sampling error that I expect in a random sample. That is a function of the variation component of the data over the square root of the sample size. So if we just think of variation again, meaning variance or dispersion in the data, you could think, well, if the variable on which a statistic, such as a sample mean or proportion, if the variable is based on something that's highly variable, high spread, high dispersion, what does that mean for the sampling error? Well, you can think of that, right? Imagine, let's just make some numbers up. Let's say that we have a square root of 1. Let's make this super simple. Let's say our denominator here is 1 and our variation component is 1. Well, 1 divided by 1 is 1. Let's say our variation component is 10 over 1 as our square root. 10 divided by 1 is 10. So you can see from that if we pick some random square root to hold constant here, that as we increase the size of the variation in the data, as we increase the size of the variation component, our sampling error gets larger. So this tells us that the more variance that we have in our data, the more variation there is in something that we're trying to measure, the more error that we're going to have in estimating that. To address the denominator here, the denominator here, the sampling size component, is the square root of the sample size. Pretty easy to comprehend, denoted in lowercase n here. So just to talk about this formula a little more, again, the conceptual formula for random sampling error being the variation component here over the square root of n, we can think about what the effect would be on our sampling error if we're to change the size of n, to now change the size of the denominator. We saw on the last slide that as the variation component, as variance increases, as our numerator gets bigger, generally the more error we'll have in our estimates. But what about the denominator? So you can think here of what would be the effect on sampling error if we increased n from 100 to 400. So imagine, let's just pick a number. Imagine that the variation component, the numerator, is 100. Well, let's take some square roots. Dividing by 10, which is the square root of 100, and then 20, which is the square root of 400, reduces error from 10 to 5. If we increase n from 400 to 700, and we take those square roots, that reduces the error from 5 to 3.8. If we increase from 400 to 1600, that reduces error from 5 to 2.5. So you're seeing here that to cut sampling error in half just with sample size, and you might think of that as, well, to cut the margin of error of a poll in half from, say, 2 points to 1 point, what do you have to do to the sample size? You have to quadruple it. So think about that diminishing marginal returns on sample size that I showed you earlier. This is really what is driving that. That in order to cut just make this simple, in order to cut the margin of error of a poll in half, you have to get 4 times as many people into the poll. That is super expensive, right? So think about the difference between a survey of 500 versus 2,000 people. That is a lot more time spent on the phone, paying people at call centers to be calling people who hang up on them, and you're paying those people at least minimum wage. That's a lot more time spent trying to get people into the sample. Even if you're going to do this cheaply as, say, a web-based sample on the internet, that's a lot more time that you spend with your survey out in the field, paying professionals to manage it. Given response rates, it's a lot more emails you have to buy and so on and so forth. So getting more people into the survey is super expensive. But you can see here that if we have to quadruple the size of a survey, quadruple the size of the sample just to cut our margin of error in half, that you really understand why most surveys, national samples in particular, are under 1,000 people, because it's just not worth it to increase the sample size to the point where you get a really larger reduction in error over what you get from like 1,000 people. So this slide here is really illustrating a lot of what I've talked about with sample sizes and why we have the sample sizes that we tend to have in national surveys. So before I push this a little more and talk about the numerator a bit, so let's go back to our formula and talk about the numerator. Again, the conceptual formula for random sampling error, or expected sampling error, is the variation component divided by the square root of n, which is the sample size and pretty easy to comprehend. For most variables in statistics, when we actually then think about, well, what are we going to use for the numerator? What is a good variation component? We typically use the standard deviation as the numerator. So we can alter the formula that we have here and actually now substantively fill in what the variation component is. So we can say that expected sampling error is the standard deviation over the square root of n, or sigma over the square root of n. This should be very familiar to you by this point in the class. Another term that we use to refer to expected sampling error or random sampling error is standard error. So when I say standard error, I'm referring to this expected sampling error. So we can most simply represent this formula as standard error equals sigma over square root of n, or standard deviation over the square root of the sample size. This slide is simply refreshing for you how we calculate the standard deviation. This is all content from before the midterm. Not going to walk through it step by step, but these are the steps for calculating that, and I'll apply that on the next slide. This slide is again review for those of you who need additional review of standard deviations. This is an illustration of calculating the standard deviation in a population. Here, we're imagining that we have a very small population of just 5 numbers. We're not taking a sample, 3, 12, 10, 12, and -4. And we are showing here how you would calculate the standard deviation if this is the population from step 1 through here, step 6. Again, review from before the midterm. You can walk through this. Not going to go into painful detail about this. And again, here, this is also review. So for those of you who, again, need more of a refresher on standard deviation, this is an illustration of how we would calculate the standard deviation in a sample. So let's take that set of 5 numbers that we just saw, 3, 12, 10, 12, -4, and let's imagine that instead of a population, it is a sample. There is a small modification to this formula that you see at the bottom, which is the subtraction of 1 from the sample size. Remember, back before the midterm when I talked about standard deviation and introduced this to you, how I discussed that sometimes we treat populations and samples a little differently. Sometimes there are slightly different formulas for calculating the same concept in a population versus a sample, and you see that here, whereas on the previous slide I didn't subtract 1 from the sample size in the population. Here with a sample I do subtract 1. This is akin to how we often use different notation, different Greek notation, in talking about a population versus a sample. So, we do treat the two things differently, but again, this is all review from before the midterm. If you don't quite remember the calculation for standard deviation, this will walk you through it for a sample. So now that we are able to calculate standard error, what the hell do we do with it? How do we use it? So again, standard error is an estimate of how off we typically would be given a random sample. How off typically might we expect the sample estimate to be from the population parameter. So let's put this in the context of an election poll. So if the proportion of primary voters who support Joe Biden for president is 0.17 or 17%, it's obviously higher now. He's crushing Bernie Sanders in primaries. But let's just imagine it's 17%. And let's imagine that there's a standard error of 0.03 or 3%. So we might say that we expect support for Biden is 17%, give or take 3%, which gives us an interval of 14% to 20%. Now, to be safe, what we typically do in statistics is we give or take 2 standard errors on each end. So 2 standard deviations above and below our estimate would give us 11% to 23%. So this plus and minus 2 standard error rule, it's common for another reason that we're going to learn about shortly. But related to statistical significance mainly. We haven't really talked about that yet. But I think in short, to give you an answer that you can recall later when we do talk about that, this 2 standard error interval has a 95% probability of including the true population parameter. So if we were to come back to this example and say we estimate that Biden's support is 17%, but 2 standard errors on each side gives us an interval from 11% to 23%, then the smart way, the correct way to interpret this poll is that while we estimate that Biden's support is 17%, we understand that we should not expect a sample to give us a precise estimate without error. So even though the estimate is 17%, there is a 95% chance that Biden's true support in the population is somewhere between 11% to 23%. And that would really be the correct way to interpret that estimate of Biden's support in this poll. So let's bring this back to that 2012 election. Let's go back to the central limit theorem now, and hopefully your mind is not exploding too much with math at this point. I only have a bit more to show you, but let's explore the second element of the central limit theorem. We've seen the first element illustrated and taken out to its logical conclusion, the standard error, which is very useful for us. The second element of the central limit theorem tells us that knowing that X bar, or our sample estimates, have a normal distribution if we take a lot of samples, and that those are centered on the population parameter, or the true mean, with a known standard error, that means that we can calculate the probability that any particular sample estimate, X bar, is within a given distance of mu. Let's explore that on the next slides. So in talking about this second element of the central limit theorem, it's useful to bring some language in here, and that is to talk about standardizing or standardization, which becomes very important because your book is really illustrating this second point in terms of the z-score and t with the t-table. So let's just get very basic about what that is and bring that back to something you've seen already. So when we're talking about a variable, it is sometimes helpful to use standardized units to talk about that variable, to talk about the observations of that variable, rather than the actual way in which it is measured. So variables have different metrics like age in years, income, temperature, exam scores, which are percents. All of these we can standardize, say, for example, in terms of talking about standard deviations, which you've seen, and how with a standard deviation, we can say that a certain percentage of the scores are within 1 and 2 standard deviations of the mean in each direction. So, for example, if the average PhD takes 6 years to complete with a standard deviation of 2 years, let's say it took me 4 years, which I wish it did, it actually took me 6, but let's say it took me 4 years. I can also say, given those data, that it took me 1 standard deviation less than the mean to complete my PhD. So here in this case, mu would be 6, sigma would be 2. So my time to completion in standardized units, or a z-score, as your book talks about, is -1, since 4 is 2 less than 6. 4 is 1 standard deviation less than 6. We can calculate the z-score here by subtracting the mean and then dividing by the standard deviation. So you can see that illustrated here, where z equals x minus u over sigma. We plug in the numbers here and we get -1. So here I have standardized this calculation. So here what I want to illustrate for you is that when we standardize data, when we standardize a variable, and by that I mean transforming it from its original metric into something that looks like a normal distribution, which you see here, that's useful for us because we know the properties of a normal distribution. We know the mathematical properties of a bell curve. And that becomes very useful as the foundation for some of the things that we're going to talk about later in this course, particularly statistical significance. But let's just imagine here that we have a normal distribution, we have a bell curve with a mean of 0. Really the thing to hone in on here is two z-scores in either direction. And you look at what that encompasses at the -2 to the +2. This is 95% of our distribution. Two z-scores take from the mean or a sample estimate is 95% of the distribution of our data, which leaves us 5% that is split on either end. 2.5% to the positive direction, 2.5% to the negative direction. So here we're seeing when we have a standardized variable, and it's standardized meaning it's a bell curve, it's a normal distribution, we know the mathematical properties of that. We know that two z-scores from the mean or the sample mean is 95% of our distribution, and that can be very useful for us for then making some mathematical inferences later. I want to show you an initial application of what we saw on the previous slide with the normal distribution and the z-scores, and how two z-scores take in 95% of the distribution of our data. Let's see an initial application of this with what we call confidence intervals. Typically, just to throw this out, and you'll understand more of this later, we often talk about a 95% confidence interval. And so what do we mean by that? What we mean is a lower and upper boundary that we calculate so that we can be confident that the parameter we are trying to estimate is between that upper and lower boundary. So for example, let's go back to that Obama-Romney matchup. The sample told us that Obama led Romney 49-47. But remember how we said that the intelligent way to interpret that was to say Obama's estimated at 49% plus or minus 6%, so that we could be confident that Obama's true support in the population when matched up against Romney was somewhere between 55 to 43%. So in that case, that's a really good illustration excuse me, of a 95% confidence interval and how we're saying Obama's true support in the population is in that range. And that's exactly illustrating what I'm showing you here. So if we take many samples of the same size, and those are randomly drawn from the population, and a 95% confidence interval is calculated from each, we can expect 95% of those to contain the parameter that we're estimating. But that's not how this typically works. We typically don't draw many samples as we did, for example, in the exam score case. In fact, we typically just use one. But the logic here is fundamentally the same, of using one sample versus repeated sampling. So here we can actually illustrate a formula for the confidence interval, which is x bar plus and minus z times the standard error, which is sigma over the square root of n. Now, I said that typically we use the 95% confidence interval. Again, we haven't talked about statistical significance yet, and that's because we're building on that math. We'll get there. But when I say 95% with the confidence interval or statistical significance, basically what I'm saying is that we want to be 95% confident of our estimates. And in the social sciences, that is a rule of thumb that's often used of how right we want to be with our estimates. That said, there are cases when sometimes we might choose a different level of confidence, typically 90% or 99%. Now, why might we do that? It really comes down to sample size of what it is that we are talking about. And generally, as a rule, the larger our sample size, the higher the higher confidence we should be able to have in our data. The lower our sample size, the smaller our sample size, oftentimes the less confidence we're able to have in our data. Well, why is that? So sample size, your n, gives you what's called statistical power. The larger your n, the more ability you have to confidently detect patterns in the data. And so this is why people in different fields of research might choose to talk about their data with different levels of confidence based on how many people are in their study, for example. So to illustrate this, let's talk about a lot of medical studies. A lot of medical studies are very expensive, sometimes on very tailored populations, and they don't have that many people in them. A very common medical study might have 30 or 50 people in it. That's not a lot of people. So if I have a study without a lot of data points with a small n, I might say, well, I have less statistical power with a smaller n, so let me use a 90% confidence interval, or let me talk about statistical significance with 90% confidence in my findings, because I don't have as large of an n. But if you have a larger n, say 100 or 1,000 or something in between, that gets us more in what we typically might think of as a 95% range. Over in the hard sciences, where they deal with molecules or interactions, often their data points are not people, and they have a lot more data points oftentimes in their studies. And so they have kind of the opposite problem of they have so much data that it's really easy to find statistically significant relationships. And in fact, it can be too easy to find relationships in the sense that they are often reporting that relationships are real, when in reality, they might not be. So if you're doing a kind of study where you have a lot of data points, you might choose to have a 99% confidence interval or a 99% level of statistical significance. So just know that we can talk about our confidence in our data, our confidence of where the population parameter is, with different levels of confidence, typically 90, 95, 99. We're typically going to use 95% in this class. But the reason that we might do that really comes down to sample size, and the typical way of talking about that will vary a lot based on what field you're in. But let's look here at the 95% confidence interval. The 95% confidence interval, we could express this formula above as x bar plus or minus 1.96 times the standard error. For the 90% confidence interval, that is 1.65 times the standard error. For 99% confidence interval, that's 2.57 times the standard error. Well, where do these values come from? So if we go to the Z table, which your book talked about a lot, we see that the proportion of the curve above the absolute value of Z is half of the confidence interval that we want to estimate. So for 1.96 in the Z table, we see that 2.5% of the distribution of the curve, of the normal curve, is above Z. And remember, since the normal curve is symmetrical, it's bell-shaped, that means that 2.5% of the distribution is below. So with a z-score of 1.96, that means that a total of 5% of the curve is outside of the interval that we're calculating. 2.5% above, 2.5% below. Thus, a 95% confidence interval. Here is the z-score, which I stole from the book, and you can see this illustrated as I just talked about on the previous slide. If you read the table and you have 1.9 on the left and you go over and you fill in that second decimal of 6, you see with 1.96 we have 0.025. So that is 2.5% of the curve above, 2.5% of the curve below. So that's why we are using 1.96 as our z value here, our standardized measure to get that, our standardized value to get that 95% confidence interval. So here, let's see this applied to a hypothetical example. Let me complicate this a little bit by making some points that your text brings up that hopefully will become clearer with this. One issue is that we don't usually know sigma. Now, if you're keeping your Greek notation strictly delineated here, you know that sigma in the Greek letter is the standard deviation in the population. But we typically don't know the population, we don't observe the population, which introduces a degree of uncertainty. We can, however, calculate the standard deviation in the sample, which is S. So just to clarify, we use the standard deviation in our sample for making our formulas work because we don't actually know the Greek letter sigma. There's also a complication with sample size with the z-scores, and that is that for a large sample, S is actually a really good estimate of the standard deviation. So this issue is not particularly relevant for larger sample sizes. And again, this is a point where I'm not showing you some math that if you go on to grad school you'll get into. But in smaller sample sizes, there are some issues with using a sample standard deviation that might make us have to use a different type of standardization other than the z-score. Instead, for our small sample sizes under 100, we might use what's called a student's t-distribution and talk about t-scores rather than z-scores. I'll talk about this because your book talks about this, and I will talk later about a t-test in this class, but really we're largely going to be talking about the z-table and z-scores. Still, I want you to understand this and its implications. This is a really important point to make, again, a lot about medical studies. You think about medical research happening right now with a lot of public health issues out in the world. The difference between a z-score and a t-score is very important in medical studies that often have sample sizes less than 100. So let's put this out there and discuss it, even if we're largely going to be discussing z in this class. So this is the student's t-distribution, often called the t-table, which I stole from the textbook. Your text actually has a pretty good discussion of this. So again, with smaller samples, typically under 100, we're going to use t-scores rather than z-scores. In calculating or in using the t-table, we need to be able to calculate something called the degree of freedom, which is n minus the number of parameters that we're estimating, n being our sample size. If we're estimating one parameter, so that'd be n minus 1. And then, again, as your book discusses, we can use the degrees of freedom to match up to the area under the curve and find the appropriate t-score here. And you'll notice here, this being table 6.4 out of your book, that as degrees of freedom increase, the value of t that marks the boundaries of the confidence interval decreases. So the more degrees of freedom you have, that means the less random sampling error you have, and the more confidence you have in your sampling statistics. So, really right now with t, just know what the difference is between z and t and when we'll use it. And I will come back to this later when t becomes relevant at one point later in the class. But again, we're mostly going to be using z and talking about z-scores and using the formulas that I showed you earlier for the 90, 95%, 99% confidence intervals based on the numbers that come from the z table. So last slide here. I know I have thrown a lot at you in this lecture, and I would have much rather thrown it at you in class over the course of a couple class periods face-to-face, but it is what it is. And I would urge you to go back and listen to this audio again as much as you need and send questions to clarify. It is very critical that you understand this content because the content every week forward is going to build on this. So if you think about what you should have grasped in this lecture, you should now be able to connect a lot of what we learned pre-midterm to the idea of statistical inference, especially that random sampling error is unavoidable and that it is preferable, in fact, to systematic error or systematic bias. But we should also account for that random sampling error when we make estimates from samples, which is exactly what we did when we talked about how to correctly interpret an election poll here. You should have learned that our estimates must incorporate a degree of uncertainty about population parameters, thanks to the sampling error, and that we can express this in terms of confidence intervals derived from z and also t-scores using formulas. So that's it for this week. Listen to this lecture again, send questions. I would highly recommend as well that you go back and read the chapter again after listening to this. Remember, read the chapter, listen to the lecture, go back and read the chapter again. Best strategy for really mastering this content.